Hi everyone, welcome to this tutorial on how to create a time-lapse movie of Hubble's variable Nebula based on the different data contributions of the bed members. Okay, so in the first step we obviously have to download all the bed data from the bed homepage. I have already done that and compiled the data here in this folder 01 register. And as you can see, despite the quite crappy weather this season, we have covered actually the activity quite nicely from the end of August of 2022 to the end of February 2023. So let's take a closer look at all these contributions. So I have opened them already here in the blink tool in PixInsight and applied a histogram transformation so that we can compare them a little bit better. And as you can see, the data quality varies quite significantly. So in some cases we have no gradients in the image, then we have quite simple gradients, or we have really complex gradients. Then there are some contributions who had problems with dust donuts. But overall the data quality is quite good, but we have to apply specific processing steps to some of the contributions. So especially if you have really complex background gradients, then you have to apply a DBE individually designed for this specific contribution. So it's not that easy that we can automate the process entirely. So I want to show the different processing steps that I typically apply for one contribution, and that is actually this contribution here by, where was it, General I row. And the reason why I chose this contribution is because it was actually the best contribution in this season. So I applied here an automatic stretch to the image, and you can see the image quality is really amazing. You can see Hubble's variable Nebula quite clearly. There are no problems with the stars, they're really round. And you can also see some of the fainter stuff here in the background. Here in this area and all these background nebulosity quite well. So signal to noise ratio is really amazing. Now the first step that I would typically apply for the other not so perfect bed contributions is to apply a dynamic background extraction. So depending on the complexity of the backgrounds, you have to design a dynamic background extraction specifically for this contribution. In this case, I don't have to apply DBE because the backgrounds seem to be quite uniform. So I will use this example now, and I don't have to apply a DBE. The next step, I apply a fast rotation. So I simply rotate the image by 90 degrees. See here, 90 degrees clockwise. And then I crop the image a little bit more. I use this process 36. I simply do that to make this image consistent with the time-lapse movie from last year. So this is not really necessary, but in order to make it consistent, I apply these steps so that I get this really nice framing, which by the way is quite nice. You should not really zoom too much into Hubble's variable Nebula because the data quality sometimes is not really good. So you will not really see a lot of features in the nebula if you zoom too much into the images. So this seemed to be quite nice. Next step, I apply some exterminator magic. So we start with BlurXTerminator, and I apply it here to this linear image. And here you can see all the different parameters. I used the parameters that Adam Block has used in a processing tutorial, I think related to M42. So simply copied his parameters, and they seem to work quite nicely also here for the Hubble's variable nebula contributions from the bed. Okay, so that takes a little bit of time. And now we can compare before and after. And as you can see, the star sizes are significantly reduced by BlurXTerminator. And also the details in the nebula are quite nicely recovered by BlurXTerminator. So this worked quite well. So in the next step, I want to go from the linear stage to the nonlinear stage, and I apply simply a masked stretch, which are more or less the default parameter, I think, beside this target background value here. So I apply the masked stretch and remove the outer stretch, and this is the result. And it looks quite nice. Yeah, so the background is quite dark. The only thing that's not working so nicely, at least for the brighter stars, is that the brighter stars are clipped. Yeah, but actually it only seems to be affecting this one bright star over here. So you have to keep that in mind, that the masked stretch might be not ideal to produce really reasonable star shapes. But what you can always do is manually stretch the stars and remove the stars from this image, and then later on add the manually stretched stars again. Yeah. So that's the magic of StarXTerminator, but I will keep these stars because they don't look too bad. Now in the next step, I have to normalize this contribution to a reference image. This is important to avoid flickering later on in the time-lapse movie. So I have to produce a reference image, and yeah, you can actually take every image from the bed. I'm taking one image from 2021. And specifically, I think I will take this image by Joel Kuiper from December 30s. Yeah. And the reason for that is because this was the best bed contribution of the last season. Yeah, you can see it's a little bit different, but the signal to noise ratio is maybe not as high as in this contribution. But that was the best bed contribution in the season 21-22. So I apply the same processing steps to the result by Joel. So I first apply the fast rotation, then I'm cropping the image, then I apply BlurXTerminator with the same settings, obviously. Okay, and then I apply a masked stretch. So now if we compare these two results, you can see that in this contribution here from the end of January 2023, the nebula is a little bit higher. The brightness of the nebula is a little bit higher in this area compared to the contribution here by Joel from the end of December 2021. So what we have to do is we have to apply a local normalization to a little bit adapt the different the brightness differences in these images. So I'm using here the local normalization module, and I'm choosing Joel Kuiper's contribution and try to apply it here to the contribution by General IRO. And the problem is there seems to be a bug in PixInsight because it claims I have not defined a reference image for the local normalization. So that doesn't work, but if we choose a different scale evaluation method, so changing it here from PSF flux evaluation to multiscale analysis, it should actually work. So it should adapt the brightness values of the contribution by general I/O to the brightness values of Joel-Kuiper's contribution. And you can see, yeah, it's a little bit dimmer now. So it is a little bit adapted to the brightness values here of Joel-Kuiper's contribution. What you could also try is to apply a linear fit in the linear stage, but from my experience this is actually not enough. So you also have to apply some local normalization to the image. Okay, and so you have to do this for every image and always use, of course, the same reference image. So this is now our reference image. Perhaps we can call this reference and then later on use it for the other contributions. Okay, so now we have applied a local normalization. Now I want to enhance the features visible within the nebula. You can see there are some brighter parts in the nebula that I want to adapt a little bit to the brightness of the fainter parts, and I also want to apply a little bit of sharpening. So the first step I typically apply is local histogram equalization with a fairly small kernel radius and a small contrast limit. The problem is when I simply apply it to this image, you can see if I compare before and after that I get a lot of artifacts in the background. Yeah? So there's something changing in the brighter parts of the nebula. You can see the darker features are now a little bit enhanced. But I don't like the difference in the background. The background becomes quite noisy. And what's also happening is the stars are quite significantly affected by this local histogram equalization. So what I will do, instead of applying the local histogram equalization to the whole image, I will first extract the stars. So I'm using now StarlessXterminator. So to get rid of the stars. So I don't want to process them that extensively, so I don't want to apply sharpening and stuff like that to the stars. So they should remain a little bit softer. And yeah, I can add them later on again, but I only want to apply the following processing steps only to the brighter and fainter parts of Hubble's variable nebula. Okay, so now I have here my stars extracted from the image. So let's call this stars. Keep the stars over here. Now the star extraction doesn't work perfectly. You can see here some stars left, but we don't care about that. We want to apply basically these different processing steps now to the nebula itself. And in order to do that, I also want to use a luminance mask so that we can really focus the processing on Hubble's variable nebula. So I'm creating a copy of this image and call it luminance mask. Then I apply a histogram transformation. So let's go to histogram transformation. And I want to darken the background quite significantly. Let's activate here the interactive mode. You can see I want to have the background really black so that nothing is really changing here. Maybe I push the white levels or the gray levels a little bit further. So that is a good starting point for a luminance mask. Now obviously there are still too many details visible in this luminance mask, and it's also quite noisy, so what I'm typically applying now is a convolution to smooth the luminance mask. So I'm applying a certain amount of standard deviation, to get something like that. Or let's go perhaps one step back. Before I apply the convolution, I will remove the stars, because I don't want to have updates in these star areas here. So I'm removing the stars. And I can do this in PixInsight using the clone stamp tool. So this is an interactive module. I'm taking a clone stamp of 70 or something like that. And then with Control and the left mouse button, I define a reference point and then simply clone stamp out all these stars that I don't want in my luminance mask. I can also remove this fainter stuff here. Yeah, that looks about right. Oh, there's another star over here. Perfect. So now I have to accept that. Always an important step that I forget most of the time. And now we can apply the convolution. So convolution. Yeah. So now we have a quite nice luminance mask. So I apply the convolution. And let's try this luminance mask. So I apply it here to our image and show the mask and don't show the mask. Yeah. So this is exactly the area where I now want to apply the local histogram equalization and the other processing steps. So be sure that the mask is activated. And now I can apply my local histogram equalization. So this is the effect of the local histogram equalization before and after. And you can see the contrast of the darker features is now significantly improved. Next, I apply HDR Multiscale Transform to dim a little bit the brighter parts here in the Hubbles variable Nebula. And I basically apply the default parameters, so that works quite nicely in this case. Yeah, you can see I have reduced a little bit the brightness here in the brighter parts. And yeah, that looks about right. You can play a little bit around with the scaling factors. So if we have larger scaling factors, we also have applied the HDR transform to a little bit larger area. So if you favor this, you can use larger scaling functions, but I think for Hubbles variable Nebula, the default values work quite nicely. Okay, and finally I apply multiscale linear transform sharpening with these settings over here. Yeah, so I'm sharpening different layers in the image. And this makes the features a little bit crisper. So this is before, after, before, and after. So this reveals a little bit more the fainter stuff and also the shadow waves that we want to resolve in the final time-lapse movie. Okay, so now I can remove the mask and save the result. So this would be now my final, more or less processed image. And now I have to repeat all of these steps for all the bat contributions. Typically, I also average all the contributions on a 5-day basis. Yeah, so if I have a lot of contributions per week, I can stack them using simply the image integration tool. Where is it? Here. Yeah, so I simply load all the files of 1 week and then apply image integration without pixel rejection, by the way, because pixel rejection introduces, in a lot of cases, artifacts, and I want to avoid that. And basically, I assume that all the bad contributions also have applied winsorized sigma clipping or something like that when they uploaded their data. Yeah, so there shouldn't be any satellite traces or stuff like that, or yeah, fixed pattern noise or something like that in the data. Yeah, so this is what I typically do. So I average on a 5-day basis if there are enough contributions. And as you can see in this season, it worked at the beginning. So in September and October, we had a lot of good contributions per week. Later on, the problem was that we had 1 to 2 contributions, and some contributions had a high signal-to-noise ratio and the other had a low signal-to-noise ratio contribution. So I had to reject the contributions with low signal-to-noise ratio, because if I have only 2 contributions, it makes no sense to stack them, especially if one contribution has a low signal-to-noise ratio. Yeah, so that's also really important to keep in mind. Now, as I mentioned before, you have to apply an individual dBE and also apply some sort of denoising, which I have forgotten, by the way. So we are not done yet. We want to apply some noise reduction here. But in this case, it's not really that important because, as you can see, the signal-to-noise ratio is quite high. But what I typically do at this step is I apply a NoiseXTerminator. Not with the default values. I think with this level of noise, we can use a denoise of 0.75. And that should get rid of most of this high frequency noise that we can see in this image. But depending on the contribution, you have to adapt this denoising step. Yeah, so 2 steps have to be adapted. First of all, the dBE and then the denoising step. And as you can see, the denoising with NoiseXTerminator works really well. So this is before, this is after, and all this high frequency noise is removed, while all the features within the nebula are still present. So this works really, really well. Okay, so these are the basic processing steps that I apply to every bad contribution. Now let's take a look how these processed image actually look like. So I open again here Blink and go into this folder, where was it, Final BV, and then this is here with NoiseXTerminator. Okay, so I open all these contributions now. And let's take a look how the result looks like. So if we now open Blink, apply nothing because it's already stretched, and I typically use an interval of 0.05 seconds. Now let's run through the contributions, and as you can see, we can already see the shadow waves traveling here through the nebula. So this is a really nice result. Yeah, there's also not too much flickering going on inside the nebula due to the local normalization that we have applied to the individual contributions. But what is flickering is the background, yeah, because as I mentioned now multiple times, the contributions are really different in terms of gradients and dust donuts and whatever is visible in the background. So you can see the background is flickering quite significantly. And what you can also see is that the signal-to-noise ratio is generally, in most cases, quite bad, yeah, because we don't have really long integration times from the individual contributions. So what I want to do next is I want to replace in each of these images the background by the background that I get when I simply stack all the bat contributions from this season and the previous season. So I should get a really a background with high signal-to-noise ratio. And I also get a static background, so I don't get this distracting flickering that is going on in the background. So I want to avoid that. Yeah, so that's really easy. So we only have to stack all the data from all the bat contributions of the different seasons, and then later on replace the nebula part in this stack. So let's do that. So this is our processed image for a given time step. And now let's stack all the data that we have acquired within the bat using simply image integration. So I'm adding here the files. So I'm taking here the 5-day averages from season 22 to 23 and also all the contributions from the previous season. Maybe except for this one here by Space Madness, because I think I have not aligned it correctly. So this is now all the bat stuff that we have collected so far. So 47 images. Again, I don't want to apply any pixel rejection. So let's integrate all this stuff. And this should produce a really high signal-to-noise ratio result. Yeah, so the background should show a lot of detail. And on the other hand, okay, I'm running out of memory. That is quite bad. So what I have to do is I save this image here. Where I'm going to save that. Saving it here. Yeah, so this is all the stuff that we have applied to this individual contribution so far. And then I will close PixInsight and will open it again. Yeah, sorry, I only have 16 gigabytes of RAM, so I have to upgrade at some time. So now I open my project again here, all the stuff that I want to apply, then I use image integration again. Okay, let's try it again with all the contributions from 2021, 2022. Yeah. And let's try it again. Hopefully I have enough memory now. Okay, it's integrating. Perfect. And because the images are quite small, it's also quite fast. So this is how the stack of all the bat contributions looks like. It's really impressive actually. So you can see all the fainter stuff that is going on here, and the nebula itself is really bright. So I apply now all the processing steps that I mentioned before. And perhaps I should call this here my master image. So this is L master. Apply fast rotation, cropping, then BlurXTerminator with these settings. And as you can see, there are only a handful of steps that you actually have to apply. Okay, and then I apply a masked stretch. Remove the auto stretch. Then I have to remove the stars again. And I deleted the luminance mask. Okay, we're creating a new luminance mask. So starless, removing the stars. So here are now our stars from our master image. So I call them stars again. Perfect. And now I'm creating a new luminance mask. That's always interesting to see it multiple times. So histogram transformation, apply to my luminance image here. So luminance mask, let's clip the black values, let's enhance this stuff a little bit. Perfect. Then I will clone stamp the stars, 50, Control left mouse button, remove this, remove this, remove this, remove this, and remove this, and maybe also this stuff here, doesn't matter I think, and apply the clone stamp, don't forget that step. And then I apply a convolution. So something like that. So it's quite fuzzy. Yeah. Okay. So this is our luminance mask again. So applying the luminance mask. And now I'm applying the local histogram equalization. I'm applying HDR Multiscale Transform and the MLT Sharpening. Yeah, so this is the processed master image, or let's say almost processed. I also have to apply noise reduction. So removing the mask. And apply NoiseXTerminator. Let's try 75 or something like that. Again. Yeah. Before, after, before, after. Perfect. So perhaps I also save my master without the stars, and I also save my stars in case the computer crashes or something like that, and I also save my luminance mask. Okay. So this is now the master of all bed contributions, and now I'm opening again the original image that we processed before. So this contribution by general I row. So this image here. Yeah, so again, this is the stack of all bet contributions over the 2 years, and this is the contribution by general I row on January the 27th, 2023. So what I want to do now is I want to replace the nebula in the master stack by the nebula here from general I rows contribution. Yeah? And when I do that for all the contributions, I get this static background over here, and therefore less flickering in the final time-lapse animation. So how can I do that? Now first I'm creating a range mask. So let's go here to range selection, go to the master, and I want to create a range mask of the area here where the nebula is located. So this seemed to be about right. Then I apply quite significant smoothness. Not too much. You can also play around here with the fuzziness, but I don't like that. Perhaps get a little bit more. So this is about the area where I want to replace the nebula. So let's create this range mask. Okay, now we have the range mask. Are there any stars left? I see here some brighter parts, so perhaps I clone stamp that stuff away. So let's try clone stamping again. Perhaps a little bit larger radius, 90 or something. Yeah, that looks better. This here, okay. And here was also a star. Yeah, that looks about right. Don't forget to apply the clone stamp. And now let's try this range mask. And as you can see, in the area of Hubble's variable nebula, this range mask is 1 or slightly below 1. And outside of it is 0. Yeah? So we want now to remove the nebula in this area and replace it by the nebula here from general I rows contribution. So I'm removing the mask, and then we apply some pixel math. So here my range mask. And I've created here pixel math with this one here, blend master. And what it does is it takes here the master image and subtract range mask times L master. So remember, the range mask is about 1 in the area of the nebula. So what this term here does is removing the nebula from the master image. And then I apply the range mask to the contribution here by general I row. So it will only affect the area of the nebula where the mask is 1. And then I will add it to the luminance master. Yeah? So what this equation actually does is removing the nebula from the master image and then adding the nebula from general I rows contribution. Yeah, so we will have all the changes within the nebula, but the background will be static. And this is what we wanted to achieve with this approach. You also have to be sure that you're creating a new image. Okay, so now we simply have to drag and drop it to the target. So this is this $T, and in this case it's the image by general I row. Yeah, so it doesn't look really different, but if we compare now the master stack with this image where I replaced the nebula in the master stack by the nebula from general iRose image. So if I activate this window and overlay it with the other window and then use Control and scroll up and down, you see there are differences. Yeah, you can barely see, especially here in this area. Perhaps you can zoom in a little bit more. Yes, I'm zooming into the nebula and apply the same zoom here to the master image. And then I compare them using Control and the down key, scroll down. You see there are some changes, and that is basically the shadow wave that you can see there. So it has done exactly what I wanted to do. So we can also compare it here with the original image from General iRO. So there should be no difference now, or at least smaller differences. And as you can see, the only thing that is changing is the background. Yeah, but the nebula itself is exactly the same. Yeah. So this is now General iRO's contribution stacked into or blended into the static background from our L master. I hope this is more or less clear now. Yeah. So by doing that, we can now stabilize the flickering in the background because we have replaced it by a static background. And in the last step, we can now add the stars again. Yeah, so I'm closing here the L master, General iRO's contribution. And this is now the image that I will put into the time-lapse movie. However, I also have to add the stars again. So let's resetting here the pixel math and apply pixel math. So this is called, let's say, L blend, because this is the master image with General iRO's contribution blended in. The pixel math is quite simple, so you simply have to combine L blend, so the starless image with the stars. So that's this image here. Yeah, these are the stars from the master stack of all bed contributions. And then operation screen, something like that. And we can create a new image, and let's do it. And yeah, really nice. So we now have the static background, the stars, and the variations in the variable nebula. Okay. So actually quite easy to apply to all these different contributions. Now to see the effect on the background, I am opening Blink again. And let's see at how the result looks like. So this is from 2022-2023. Yeah, so these are all the contributions where I applied all the previous processing steps and then replaced the background in each contribution by the background from the master stack. I think I used a little bit different stars in this image, so let's turn the auto SDF off and run the animation, and you can see now the stars and the background are obviously static, and the only changes are occurring within Hubble's variable nebula. And you can also see the shadow waves are now really nicely visible. Yeah, so that's basically the basis for the time-lapse movie. Now I can simply export all these contributions here from Blink into PNG files. There's also a script for file conversion. So you can use here this movie icon to export all the contributions here into a separate folder. I call it here 006 movie. And if you run that, it will simply convert all these XISF files into PNGs, and then you get an error message if you have not installed here FFmpeg. But the most important part is that you get the PNG files. So let's take a look here, 006 PNG. You can see here are now the PNG files of all the different contributions. And we can now merge all these PNG files into an animated GIF, for example using pip, which can be downloaded for free. So you simply add the images for which you want to create a time-lapse movie. So Blink 1 to 19. Okay. And then under animation output options, you're choosing animated GIF, maximum quality, and I typically use a frame rate of 18 frames per second. Yeah, that should work, and then simply start processing. And then this folder should pop up pip something, and there you have your animated GIF. Yeah, so these are the basic steps on how to process the Hubbles variable Nebula data from the bed into a final time-lapse animation. So hopefully this tutorial was useful for you. I thank you for your attention, and I see you in the next tutorial. Bye for now.